Welcome, everybody. My opponent, Professor Marc, the committee, Ambra, Sannino, Professor Johan Driesen, and Professor Nando, Kaminski. And welcome all of the others who are connected online and those who are sitting here in the room with me. I will now give an introduction to the work I have been doing in the last 5 years here as a PhD student at KTH University. This project has been funded by Swigridge, Hitachi ABB, and the Swedish Energy Agency. High voltage direct current, in short HVDC, is the state-of-the-art technology for transmitting electricity over large distances or through difficult terrain. In the latter case, a cable has to be used, for example, for offshore wind farms. Converters are needed to integrate the DC cable into our already existing alternating current grid. The waveforms of current and voltage in the AC side are sinusoidal shaped, whereas the current and voltage on the DC side is constant. HVDC grids are envisioned to span whole continents in the future, forming the backbone of our global electricity grid. However, until that happens, a lot of challenges have to be faced. In Europe, HVDC connections are used for the integration of remote renewable energies. For example, wind power, hydropower, solar power, and geothermal power. Each dot on this map represents a conversion point, hence a converter, and the requirements for these converters may vary, but are usually low volume in size, cost efficiency, and reliability. In order to have an impression of the size of such installations, I show you here the in-Elfe converter station. Just as a comparison, here on the left side, you can see 3 little vans parked. And this should give you the impression that this converter station is actually quite huge. You can see here on the AC side, the 7 single-phase transformers. You can see the arm inductors here. You can also see the converter hall, which is the focus of this thesis. And you can see the cooling equipment. The state-of-the-art technology for HVDC voltage source converters is the modular multi-level converter, in short, MMC. And also here you get an impression of the scale by looking at this person, which is standing here between the converter arms. Each MMC consists of several submodules. Each submodule, among other components, consists of power semiconductor devices. And each power semiconductor device may consist of several semiconductor dies, or also of a monolithic wafer. We have published on different levels of this hardware hierarchy, and this includes converter design and layout, submodule functionality and topologies, semiconductor devices, and one review combining all of these fields. Now I will just go quickly through the publications. In publication 1, we developed a toolbox for modeling semiconductor device losses in EMTP-RV. This was contributing to the ability of EMTP-RV to study power electronic systems. In publication 2, we have looked at the application of ultra-high voltage power semiconductor devices for modular multi-level converters. We identified benefits regarding converter complexity, volume, and losses. In publication 3, we have proposed a novel method for handling submodule internal faults. In publication 4, we have investigated internal surge currents of the semi-full bridge topology. We have also built a full-scale laboratory setup, and we have investigated techniques for capacitor voltage balancing, which contributed to a controller. In publication 5, we have looked at a novel submodule cluster with low conduction losses, and we have found silicon carbide MOSFETs to be very suitable for such an implementation. In publication 6, we offer a comprehensive review and evaluation of submodule topologies. The focus here was the implementation with different silicon carbide power semiconductor technologies. The evaluation in this paper is based on a list of defined technical requirements for modular multi-level converters. Publication 7 was kind of a different topic. In this case, we investigated differently charge carrier lifetime tailored silicon carbide pin diodes, and these were for an application in high voltage, high frequencies LCC converters. The requirements for HVDC converters are different ones. In this case, the core requirements, we define them as grid code compliance, reliability, and cost. In publication 6, we proposed 10 technical requirements in order for our evaluations. And these requirements are sufficient harmonic performance, DC side fault handling, robustness, internal fault handling of the submodules, low complexity of the converter, high efficiency, maintainability, low semiconductor cost, low energy storage, which is related to the size of the capacitors, and a small footprint. Some of these requirements are mutually exclusive, so they can also be subject to trade-offs. The rest of the presentation is structured as follows. First, I'm going to give an introduction into modular multi-level converters. Then we're going to have a look at the first big topic, which is submodule design with bipolar silicon carbide devices. The second big topic is the optimization of bipolar silicon carbide diodes. And the third big topic is submodule design with advanced topologies and unipolar silicon carbide devices. At the end, I will give a summary and a conclusion and propose some future work. A simplified model of the modular multi-level converter can be seen here on the right. I marked a converter arm, and in the equivalent circle, you can see that one converter arm consists of the arm inductor and a variable voltage source in this model. This variable voltage source models a series connection of submodules. Each of these submodules can either be inserted or bypassed. And by doing that, the capacitor of the submodule can be either contribute to the arm voltage or not. If we then have a certain amount of these submodules, we can approximate an alternating voltage. Each of the submodules consists of power semiconductor devices and a capacitor and some auxiliary equipment. Here I'm showing one of these power semiconductor devices, and you can see that within the device, this module consists of several semiconductor dies. Nowadays, silicon IGBTs are the predominant choice for such converters. And the topic of this thesis has been the investigation of novel devices based on silicon carbide. The silicon devices used in the high voltage sector are diodes, IGBTs, IGCTs, and thyristors. Those usually have a voltage rating of lower than 6.5 kilovolts. And in HVDC VSCs, we use diodes, IGBTs, and thyristors for bypass equipment. The use of IGCTs has been proposed. For silicon carbide, however, the possible devices are MOSFETs, diodes, IGBTs, GTOs, and thyristors. MOSFETs can have, or are foreseen to have, a blocking voltage of up to 15 kV, and demonstrations for such an implementation have been made. However, for the bipolar silicon carbide devices, such as diodes, IGBTs, GTOs, and thyristors, which have a blocking voltage higher than 10 kV, no demonstration has been shown yet. For the state-of-the-art implementation, the following approach is used. We would use a silicon IGBT in a diode. Those have a voltage rating of 3.3 until 4.5 kilovolts. We would then use half or full bridge topology for the submodule and have several hundred of these submodules connected in series. Alternatively, we can series connect the silicon devices and have submodules with blocking voltages that are higher, for example, 16 kV. For silicon carbide devices, different approaches are proposed in this thesis. One would be to use silicon carbide MOSFETs, as they are already available today, maybe with a bit higher power rating. Those have a voltage rating of 3.3 kilovolts. We would use advanced submodule topologies for these, and these topologies use the parallel connection of switches and capacitors. A totally different approach is the use of silicon bipolar devices. Those can have higher blocking voltages, for example, 30 kV. And here we would use a topology with a low switch count. And this enables us to have submodules with a high nominal submodule voltage. And then we would only use several tens of submodules per MMC arm. If we use MOSFETs with high blocking voltage, we could have an approach that is somewhere between these two. The approach with bipolar silicon carbide devices is called here design approach 1. And I'm going to talk about that one first. And later in the presentation, I will talk about the design with silicon carbide MOSFETs, which is here named Design Approach 2. Now let's go into the details with submodule design with bipolar SiC devices. First, we're going to have a look at converter design and layout, and then afterwards, we're going to show one method to handle submodule internal faults. Ultra-high voltage bipolar silicon carbide devices are foreseen to have blocking voltages of up to 50 kilovolts. And this means we have a high submodule voltage and we have fewer submodules per MMC arm. In publication 2, we compared different test cases. And one of the test cases was the design with the MMC with silicon carbide GTOs of a blocking voltage of 33 kilovolts. And this would mean that we have about 42 submodules per MMC arm. And the test case here was a 1 gigawatt converter with 640 kilovolts on the DC side. And the reduction of submodules per arm enables us to have lower converter complexity. There's other advantages, lower converter losses, and I will explain this on the example of the conduction characteristic of different devices. Here you can see the conduction characteristic of 5 different silicon carbide GTOs. These are theoretical devices. And we compare those to the conduction characteristic of a silicon IGCT with 5.5 kV. And in order to make this comparison fair, I have taken the voltage on the x-axis and normalized by the blocking voltage. Therefore, we can compare the high voltage silicon carbide devices quasi to a series connection of the silicon devices. As you can see here, the red and the yellow and the green curve perform better than the silicon device. And these curves correspond to the devices with 20, 30, and 40 kV. If I remember correctly, then the lifetime for these devices should be around 1 microsecond. And this means a difference for the converter losses. We have simulated that and compared a conventional solution of a 3.3 kV silicon IGBT module, a silicon IGCT, and the 33 kV silicon carbide GTO. And as you can see, for the silicon carbide GTO, we get reduced converter losses. Regardless of the angle, all the time, these losses are lower than with the comparison cases. Another advantage is the potential of lower converter volume. In publication 2, we have proposed different converter layouts, as seen here. And for these layouts, we have investigated the converter volume. Here on the y-axis, you can see the converter volume. On the x-axis, you see the amount of submodules. And we have a second x-axis that would indicate the submodule voltage for that amount of submodules. And under the graph here, you can see which technology would correspond to such a voltage. For example, if you would design a converter with 400 submodules, then you would choose a submodule voltage of 1.6 kilovolts for the test case. And this would mean we would use silicon IGBTs. However, if we want to design the converter with 50 submodules, you would use a submodule voltage of 12.8 kilovolts. And this would mean we would choose a silicon carbide GTO. As you can see here in the graph, there is a significant potential for volume reduction, here up to 50%. Another issue that has to be considered with such a converter design is the harmonic performance. In this case, I show the total harmonic distortion on the y-axis and the amount of submodules on the x-axis. Each of these curves represents the total harmonic distortion for a certain switching frequency. And P here is the pulse number. So a pulse number of 2 would correspond to a switching frequency of 2 times the fundamental. In this case, 2 times 50 hertz is 100 hertz. And in order to avoid additional filtering for the converter, you should keep the THD below a certain level. And as you can see here, as soon as we surpass a certain amount, we can push the THD below 1%. And if that is not enough, we can still increase the switching frequency a little bit. A big issue with such a design is the higher submodule energy. And for this, in publication 3, we have compared different design cases. Here I have marked the standard solution with an IGBT with a nominal voltage of 1.65 kV. And you can see that the energy is 16.7 kilojoule, which is already quite a lot. However, for the proposed design, you would get an energy that is 10 times higher, which is critical. For those conventional submodules, we would employ an explosion-proof housing, and I'm going to explain this step by step here. For example, here I use the example of a half bridge, and if switch 2 fails and we turn on switch 1, we get a discharge of our capacitor through the half bridge. The arm current will be conducted through the bypass equipment, which can be thyristors and mechanical switches. However, the energy discharge from the capacitor will destroy those modules and lead to an explosion. And therefore, we need explosion-proof housing for such devices, for such submodules. If we use a submodule with IGCTs, we can take a different approach. IGCTs have a short circuit failure mode, which is stable. Therefore, the arm current can be conducted through the failed device. And the capacitor energy can be discharged through bypass thyristor, which is arranged across the inductor and the capacitor. However, for higher submodule energies, that can also be critical. Therefore, in publication 3, we proposed the use of a discharge loop. In this case, we arranged the bypass capacitor only across the inductor. So if a fault occurs, first the capacitor will discharge through the half bridge, as seen here. The discharge is limited by the DIDT reactor of the cell. As soon as the whole energy is stored in the DIDT reactor, which usually happens after about a quarter of the oscillation period, we can fire the bypass thyristor and discharge the energy through this dedicated discharge loop. I visualize this here in the uncontrolled and the controlled case. In the uncontrolled case, our capacitor discharges in a damped oscillation. You can see here the voltage is going down and is oscillating. The current will go up, and the peak current here are normally in the range of several tens to several hundreds of kiloamps. So that is very difficult to handle. If we then fire the bypass thyristor after 1/4 of the period, we can see that the current decreases in the half bridge and is commutated to the bypass thyristor and is discharged there. This has the advantage that only a small fraction of the total energy is dissipated in switch 1 and switch 2. This also means that the mechanical and thermal stress is isolated in the discharge loop after 1/4 of the oscillation period. It requires an extremely robust design of the discharge loop. But the thermal stress that we calculated in this publication is within the limits that IGCTs accept today. Now let's go to big topic number 2, which is the optimization of bipolar silicon carbide diodes. The application in this case was a different one. It was a high voltage, high frequency LCC converter that we ran at 50 kilohertz. The input converter was optimized using silicon carbide MOSFETs. That has been done by the work of Dian Sadik. You can see the resonant tank right here. Then we have a certain transformer design here, and that one has been discussed in the PhD thesis of Per Ranstad. The focus of this work was on the optimization of the diode rectifier using 10 kilovolt silicon carbide diodes. That is publication number 7. The particular focus here was the high frequency performance of the whole converter. And this is because if we run a higher frequency, we can decrease the volume and the cost of the passive components, such as the capacitor and the transformer. Such diodes can be also used in the HVDC converter for the design approach 1 that we have discussed before. And in this case, they would be needed as anti-parallel diodes for IGBTs, for example, or in snubber circuits or in gate drive units. Now, first, I'm going to explain the LCC converter operation. You can see on the input side, we have a square wave voltage, and we have a certain current shape. The current in these two areas here is defined by the impedance of the circuit. On the output side, however, those look a bit different. The increase of the voltage during the commutation is slowed down. And we can see in the current, there's little triangles cut out of our waveform. And this is due to the winding capacitance of the transformer. This winding capacitance is parasitic, but it can be used for the function of the converter. In this case, the voltage increase is slowed down. And as you know, reverse recovery of the diode occurs when a diode is turned off, which, for example, happens here. Since this reverse recovery coincides with a voltage that is still quite low, the switching losses can be reduced drastically. I'm continuing to show you the output rectifier here, and the rest of the circuit is blended out. And we're going to have a look at the detailed switching processes. I have marked here different effects that are happening during the commutation. We have the reverse recovery of the diode in blue. We also have the charging and discharging of the parasitic capacitors of the diode, which are marked in green and in orange. And we have the charging of the capacitor CP. So each time the polarity on the output of the transformer changes, CP is recharged, therefore takes away the charge QCP here out of our current waveform. And if we look at the switching process here on the left, during a turnoff, we see the very slow increase of the voltage. We can see the charging of the parasitic capacitor of the diode, and we also see the reverse recovery current. Those two effects here overlap, so we get the curve that is determined by the blue and green region. And as you can see here, this current peak of the reverse recovery coincides with a low voltage over the diode, thus low switching losses. As the longer we have the tail of this reverse recovery, the more the current will go into a region where the voltage is higher, therefore we will have higher switching losses. The shorter the tail of this reverse recovery effect is, the more we can move the charge into an area where we have low voltage, thus lower switching losses. For this converter, we investigated the performance with differently optimized silicon carbide diodes. Those diodes have a blocking voltage of 10 kilovolts, and you can either optimize them for conduction or for switching performance. For conduction performance, a high carrier lifetime is required. Natively, that is below 1 microsecond, and the cause for this low charge carrier lifetime are the carbon vacancies in the material. The diodes were applied with a novel charge carrier lifetime enhancement process that was done by our colleagues in Chista, which was supported by Mirtek Barkowski. And that resulted in device B, which is a conduction optimized device. Device C is a switching optimized device, which has been exposed to proton irradiation. For switching optimized devices, we need a low charge carrier lifetime. Therefore, this proton irradiation, a lifetime killing process, was applied. What is also interesting to explain here that for the conduction optimized device, two processes were happening during the lifetime enhancement. One was the carbon implantation on this side of the wafer. The other one was the thermal generation of new carbon vacancies in the rest of the wafer, which was done by the high temperature, in this case 1800 degrees Celsius. Therefore, we can expect that the lifetime is decreased in this region, but increased in the region close to the anode. We have built a laboratory setup in which we have done calorimetric and electric measurements. For both, we have put the diodes into transformer oil. This transformer oil served as a cooling medium, but also insulation medium. For the calorimetric measurements, we have placed the diode rectifier into a foam enclosure, and then we have measured the temperature increase. For the electric measurements, we have measured the current and voltage at one diode. Now I'm going to go into detail with the switching performance of these devices. On the left side, you can see the conduction optimized device, which is device B. On the right side, you can see the switching optimized device, which is device C. You can see here the reverse recovery effect as shown already schematically before, but this is a measurement. You can see that the reverse recovery peak for the conduction optimized device is much higher than for the switching optimized device. And you can also see that the current tail for the switching optimized device is much shorter. We have then used these measurements in order to fit a TCAD model. And here in these lower graphs, you see the measurement in blue and the TCAD model in green. Different time instants here are marked with the numbers 1 to 8. It's a bit difficult to see because they're quite small, but the 1 is around here on the left side and the 8 is on the right side, and the same for the switching optimized device. And this enables us in simulation to see what happens inside of the device. We are looking here at the whole concentration inside of the device. On the left side, there is the P+ layer, and on the very right side, there is the N+ buffer layer, and in the middle is the drift region. As you can see here in the drift region, the whole concentration decreases starting from the right side And the last point where the whole concentration decreases is at the N+ buffer layer. For the switching optimized device, where we have irradiated this region between 80 and 100 micrometers, you can see that the whole concentration decreases quite quickly in this area. This also has the by-effect that we have charges trapped here at around 80 micrometers, and this leads to a snappy turn-off of the diode, as indicated in the measurement by these oscillations here. You can also see a bigger oscillation afterwards. That one is due to the commutation of the diodes and is related to the inductance of the circuit. Besides the switching performance, there's also the conduction performance. On the left side, you see the conduction curve of device B and device C. We have then measured these devices in a calorimetric test and compared them to a silicon implementation. This silicon implementation is the state-of-the-art implementation, and it features a series connection of 8 silicon devices. So this device is an 8 kilovolt device. We measured losses of 21 watts in this case. And for the conduction optimized device, we measured 13 watts. And the difference between these two is 37%. So we get a reduction of the losses of 37%. Since device B is a 10 kilovolt device and the silicon stack is only an 8 kilovolt device, and if we interpolate linearly, we would get something of a loss reduction of around 50%, so half. Another interesting point here is that only 19% of the losses are reverse recovery losses. So the optimization of this device for the circuit operating at 50 kilohertz is quite good. Then we have the switching optimized device. Here we have losses of 19 watts. And you can see this is just a reduction of 12% or 28% if you make a more fair comparison. Interesting to see in this case is that only 3% of the losses are reverse recovery losses. And this means that this device would enable our circuit to operate at much higher switching frequencies. And this would enable us to reduce the passive components, such as capacitor and transformer, leading to a more optimized design of the converter. Now let's go to the big topic number 3, which is the submodule design with advanced topologies and unipolar silicon carbide devices. I will first talk about advanced submodule topologies and their functionalities. I will talk about advantages with parallel connection, and then I will give a few comparisons for the converter design. First, I want to give you a few examples of submodule topologies. The half-bridge, you already have seen it several times in this presentation. That is a unipolar submodule topology, meaning it can only provide positive voltage or a bypass. The full bridge, which is the other conventional topology, can provide positive and negative voltage. Thus, it is a bipolar submodule topology. There is other topologies, and just exemplarily, I show 2 here. One is the switch capacitor submodule. This one has 2 capacitors, therefore it can provide 2 positive voltage levels. And we also have this asymmetrically bipolar submodule topology here on the right, which is the semi-full bridge. The semi-full bridge is asymmetric because it can provide 1 negative voltage level, but 2 positive voltage levels. But why would we need negative arm voltage at all? Here in the formula, you can see the relation of the peak AC voltage of the converter and the DC voltage divided by 2. And those two are linked by the modulation index M. The arm voltage then is calculated by the DC voltage divided by 2 minus the instantaneous AC voltage. And as you can see here, if we choose a modulation index close to 1 or lower, we can only reach positive arm voltages. However, if we choose the modulation index to be higher than 1, we can also get negative arm voltage. This is illustrated in this figure here. On the y-axis, you have the voltage normalized to the DC voltage, and on the x-axis, you have the modulation index. The different curves then represent the maximum and the minimum voltage that has to be provided by the converter arm. And I plotted both arms here, the upper and the lower arm. As you can see, for a design with a modulation index lower than 1, we have only positive voltage. If we run the converter at the modulation index higher than 1, we need to design the arm with negative voltage, thus submodules with negative voltage are required. Another point here is handling DC faults. In this case, I plotted the same curves for a case of a pole to ground fault on the positive pole. And as you can see here, even running the converter at the modulation index lower than 1, we need negative arm voltage. Now let's go back to the submodule functionality. If we want to compare the semi-full bridge to a full bridge, we would need to compare it to 2 full bridges. And this is because the semi-full bridge has 2 capacitors, thus can provide 2 positive voltage levels. And the full bridge can just provide 1 voltage level. Therefore, we need 2 series connected of these ones. We can see now that the semi-full bridge has different advantages. One is the switch count. The full bridge has a switch count of 8, and the semi-full bridge only of 7. It was even proposed to rate devices S3 and S5 only half, and this would lead to a semiconductor cost of 6 switches. Another point that we can see here is that if we conduct the arm current through these submodules, we have 4 conducting switches for the full bridge solution. For example, the current going through S1, capacitor C1, S4, and then the other submodules, for example, through S2 and S3. This means that 4 devices are conducting. For the semi-full bridge, however, the submodule could be in a state where S2, S4, and S6 are turned on, and therefore only 3 devices would conduct the current. Therefore, we can expect lower conduction losses for such a topology. I had the pleasure to collaborate with my colleague and good friend Stefanie Heinig on the semi-full bridge. She defended her thesis 2 months ago, and luckily she recorded it, so I don't have to talk too much about the semi-full bridge today. Instead, you can have a look at her YouTube video, or in YouTube you can just search for Stefanie Heinig and you will find it immediately. Another feature of these advanced topologies is the parallel connection of switches in the submodules. And I will explain this on the example of the 00 submodule, which has been invented by Professor Marc at the University in Munich. If we compare this to a full bridge, we have talked about the full bridge already. The full bridge has a switch count of 4. However, the 00 has a switch count of 5. At first, this might be seen as a disadvantage. But if you look at the conducting switches, you see that the full bridge has 2. In the case of the 00, it depends highly on the switching state. If, for example, we have a switching state that conducts the current through S1, S3, and S5, we have 3 devices conducting. However, if we put the submodule in a bypass, we conduct the current through S1, S4 in parallel to S2 and S5. Therefore, these devices are parallel connected and the conduction losses can be reduced. Silicon carbide MOSFETs are specifically useful for such a parallel connection, and I will explain this on the example of the conduction characteristic. Here on the left side, you see qualitatively the conduction characteristic for different device technologies. For example, the silicon IGBT, the silicon carbide GTO, silicon carbide IGBT, and the silicon carbide MOSFETs. Interesting to see here is that the silicon IGBT has a built-in potential and then a resistive part. For the silicon carbide devices, which are bipolar, you also have a built-in potential, which is a bit higher, and then a resistive part. But for the silicon carbide MOSFETs, you can only see the resistive part. Just going to have a sip of water. If we now parallel connect these devices, either in a power device by connecting several of the dies in parallel, or in a submodule by parallel connecting different current paths, then we can decrease the resistive part of these devices. And this is indicated here in this GIF. As you can see, the loss reduction in the bipolar devices is limited by the built-in potential. However, the silicon carbide MOSFET doesn't have this limitation, and therefore we can theoretically get an arbitrary reduction of the conduction losses. And of course, you have to pay this with silicon carbide area. But summarizing, we can say that silicon carbide MOSFETs benefit from the parallel connection. This can be done on power device level and on submodule level. Furthermore, silicon carbide devices have the advantage of higher maximum temperature. And the performance of silicon carbide MOSFETs has already been compared with silicon IGBTs and has been found competitive. Now I'm going to explain why this makes such a difference in the modular multi-level converter. In order to calculate the conduction losses by a silicon carbide MOSFET, we can take the resistance times the current through the device squared, because it's a purely resistive device. Therefore, we can compare it with the arm current squared, because the arm current is the current that the devices will see in the submodule. And I have done this here for different load angles. For example, for purely active power transfer in black, and for a certain reactive power in blue and in red. Then in the figure below, you can see the share of the submodules that are in a certain state for a certain time instant. So here on the x-axis, you have the whole period of the waveforms. And if you look at the beginning of the period, you can see that most of the submodules are in the bypass state, thus the 0 VC state, which corresponds to the state that I marked here for the 00 submodule. If you go to the middle of the period, you can see that most of the submodules are in the +1 VC state. However, if you compare those two figures, you can see that the red areas coincide with the areas where the square of the arm current is quite high. And therefore, we can reduce the conduction losses quite a lot. And this leads to the result that the 00 has lower conduction losses than the full bridge, even though it has a higher switch count. There is a variety of topologies that use the parallel connection of devices, and I have shown them here. I'm also indicating these parallel paths for some of the switching states here. And another interesting thing to see is that some of these topologies parallel connect capacitors, for example, the semi-full bridge or the switch capacitor, or also the double connected 00, and all of these topologies which are essentially building on the same principle than these ones here. And the takeaway here is that by parallel connecting the switches, we get benefits for conduction losses. And by parallel connecting the capacitors, we get benefits for the capacitor voltage balancing, which is related to the capacitor voltage ripple, thus the capacitor volume and cost and size. The challenge here is now, how do we compare such a large variety of submodules with different features for an MMC design? For this, we want to find an expression for the semiconductor cost. We would also like to find an expression for the semiconductor losses. And we would like both of these expressions to be independent of the amount of levels per arm, therefore be independent of the semiconductor blocking voltage. We would also like the comparison to be independent of individual product loss data. And then we can compare different submodules with different amount of switches, capacitors, voltage capability, and so on. One of these expressions here for the semiconductor expenditure can be the arm resistance, which is the combined resistance of all the devices used in an MMC arm. In order to explain this, I will not go into the formulas, but I will explain it in a visual way. Let's say, for example, we want to design our MMC arm, and we have a fixed semiconductor cost. So we have a certain amount of semiconductor dies that is indicated here. And then we decide to compare two cases, for example, the half bridge and the semi-full bridge. According to the rating of the converter, we then decide to have 4 levels in the converter. For this, we have to divide the dies for the half bridge by 4 and for the semi-full bridge by 2, because the semi-full bridge has 2 voltage levels and the half bridge only 1. But those different implementations also have different amount of switches in the topology. For the half bridge, this would be 2. For the semi-full bridge would be 7. So we have to divide by 2 in the half bridge case and by 7 in the semi-full bridge case. This means for each switch in each of the submodules, the half bridge topology has 7 dies and the semi-full bridge topology has 4 dies. This means as if the arm current is flowing through these devices, we will have more losses generated in the semi-full bridge than in the half bridge. But how much more or less, that has to be simulated. And I did that for a variety of topology and cases. This might seem very overwhelming at first, but I'm going to guide you through this step by step. First of all, each of these curves, in each point on this curve, represent one MMC design. And for all of these designs, I have kept the losses at 0.5%. Then on the x-axis, you see the parameter K, which is a design parameter, determining the maximum arm voltage of our MMC arm. And the modulation index has been chosen equal to K. So basically, K is equal to the modulation index that this design is run at in this comparison case. On the y-axis, you see the term 1 divided by the arm resistance times the amount of levels, which is an indicator of our semiconductor cost. And then finally, I have plotted this for different semiconductor technologies: the silicon carbide MOSFET, the silicon and silicon carbide IGBT, and the silicon carbide GTO. Now, if we have a look at how these submodule topologies perform, it might seem very messy, so I'm just going to group them for you. We have our unipolar submodules here in the bottom part, so they have a quite low semiconductor cost. However, they cannot be operated at a modulation index higher than 1. Then we have the asymmetrically bipolar submodules here in the middle. And we have our bipolar submodules with the highest semiconductor cost here in the top. I have marked here for you, for example, the 00 submodule that I introduced earlier. And as we can see here, the semiconductor cost of this topology is highly dependent on the technology that you use. And this is simply due to the fact that the parallel connection is very beneficial for an implementation with silicon carbide MOSFETs, but a bit less beneficial for the bipolar devices. And therefore, you can see that the semiconductor cost for the 00 is lower in this case than the full bridge, but higher than the full bridge in the other cases. I also marked here for you the double connected 00, which builds on the same effect. You can see this one has much lower semiconductor cost, but it's also dependent on the device technology used. Interestingly, the semi-full bridge between the modulation index of 1 and 1.5 has quite a stable semiconductor cost. Therefore, it is independent of the technology used here. We have compared this variety of submodules in publication number 6, and we have created this comparison table. We will not go through all the details, but what I can say is that we compared the submodules based on their structure, their voltage capability, their features, and we did an evaluation of control complexity, design complexity, and power loss. I will just mark for you our conventional topologies, which is the half bridge and the full bridge. You can see the losses for the half bridge are quite well, but we know that the half bridge has a reduced functionality because it's only unipolar submodule topology. For the full bridge, we get the full bipolar capability, but it has disadvantages regarding the losses. I've also marked these two advanced topologies, which are quite promising, which perform somewhere in the middle between these two conventional ones. Now I will give you a summary and a conclusion of this work, and I will propose some future projects. We have talked about ultra-high voltage bipolar silicon carbide devices. We have seen submodule internal fault handling with the discharge loop in publication number 3. We have also talked about converter design and layout, and we have seen that there's potential benefits regarding volume, complexity, and losses. The second big topic was silicon carbide MOSFETs. We have looked at advanced submodule topologies, the parallel connection of switches, and we have had a short look at the semi-full bridge. The ARM design for such an approach leads to lower losses or alternatively lower semiconductor cost. We also maintain DC fault handling by providing a negative ARM voltage, and we can also provide lower energy storage by reducing the capacitor voltage ripple. The last big topic was the optimization of 10 kilovolt silicon carbide diodes. These diodes replace a series connection of silicon devices, and we have shown the optimization of these devices regarding conduction and switching performance. Concluding, silicon carbide power semiconductor devices enable system-level benefits, and I will just show this shortly on the example of the technical requirements that I introduced earlier. The design with bipolar silicon carbide devices with higher than 10 kV offers converters with large-sized submodules. Those can have lower complexity, higher efficiency, and a smaller footprint. The discharge loop, which has been a topology feature, enables increased robustness and internal fault handling. Unipolar silicon carbide devices enable to use synergies with certain advanced submodule topologies. These topologies use the parallel connection of switches and capacitors. And by this, we can satisfy the requirements DC fault handling, complexity, high efficiency, low semiconductor expenditure, low energy storage, and a small footprint. The semi-full bridge topology is a very interesting topology to suit these demands, and it also has benefits for DC side fault handling, high efficiency, low semiconductor cost, low energy storage requirements, and small footprints. And we have seen the performance optimization of 10 kilovolt silicon carbide pin diodes, which feed into the design of approach 1, which is the design with bipolar silicon carbide devices. Merits for the designs of MMCs with silicon carbide devices have been discussed here, but there are a variety of challenges remaining. One of them specifically is the current sharing during power connection of silicon carbide MOSFET modules. We have seen in preliminary tests that the current sharing is not ideal, and this could be fixed by additional driver functionality. And by this, we could balance out the differences between different modules, but we could also handle differences for differently aging modules in these submodules. Another point could be the air cooling of HVDC converters. And this could be done by a massive overrating of silicon carbide MOSFET switches. And even if an air cooling in the end is not an option, it is very interesting to investigate which kind of headroom we can create by using overrating silicon carbide MOSFETs for creating headroom for the cooling equipment. A third topic could be to investigate novel packaging technologies for ultra-high voltage bipolar silicon carbide devices. A specific problem for these devices is the high power density and the voltages for these devices. And there has been a few packaging solutions proposed, but none of these packaging solutions tackles high power devices. Now I would like to thank you for your attention, and I hand over the word to the chair and the opponent and the committee for asking questions.
Thank you very much.